Now it's for sure posted. So we are doing a review today, yes. So let me really quick give you guys a rundown of what's going to happen today. I tried to make an agenda, but it was being annoying, so I just ditched it. So basically, today we are going to spend maybe 5 minutes on chapter 19. I have it up on the screen right now. I know it's a picture of notes. I did it on paper. I don't know why. But then we're going to spend a majority of the time going through the extra credit practice final. And I'm going to run through that with you guys because I think a lot of those questions are really valuable. And getting a chance to put everything together is really valuable. So that's the plan for today. And I'm going to send you guys the attendance link. For some reason, it's being annoying, so I might just have to send that at the end, but that is A-okay. All right, so right now on the screen, as I mentioned, this is chapter 19. So we have two reactions, the aldol condensation and the Claisen condensation. And the reason I'm not going to spend too much time on it is because I still haven't heard back from Dr. West, and I'm not sure if this will be on your exam. And honestly, these are both really long mechanisms, so I don't want to waste a lot of time on it. And even if it does show up on your exam, it'll be like maybe one question. So I think it would be more valuable to just give you these notes just so you've seen it before and then actually spend time on everything else. So what I want you guys to take away from this is mainly that in this kind of reaction, it's only going to happen with an aldehyde and ketone, and it's essentially going to be the reaction of an aldehyde or ketone with an alkoxide molecule. And then it's kind of going to be like chapter 18 where we make the enolate. And once we make the enolate, we're actually going to react it with another molecule of itself, which is what is shown in step 2. And then basically from there on, it just kind of like cleans up itself by reforming the double bond or protonating. In this case, we decided to protonate and make an alcohol. And since we made the alcohol, it can react with the carbonyl. It can undergo a condensation if you add heat. And we can kick off the OH. So this is kind of different than heat in chapter 18 because now instead of doing a decarboxylation, all they're doing is an elimination and they're getting rid of the OH. So that's the main concept. If you guys want to take a screenshot of this, I will also be sending it to you in an email probably tonight, if not Monday morning. And so, yeah. I don't know why that was such a long-winded way to say that, but that's pretty much it. Any questions on that? English is really hard today. I don't understand why, but it's cool. We got this. Okay, so I am going to switch over to the practice final. Unless anyone has any questions about chapter 19, the condensations, things like that. Okay, that's a really good question. So someone asked, what would you recommend about completing chapter 19 for Orion? So here's the thing. Most semesters, he will give chapter 19 as extra credit on Orion, but not every semester. And so if he doesn't make it extra credit, it's part of your grade. So I'm always going to say do it. There's ways to get around Orion to do it faster so it doesn't take a million years because Orion isn't the most helpful thing. I'm not recommending you do that, wink, wink, but like, you know, finish it, but you don't have to like go crazy, like trying to do every single question and understand every single question, you know, things like that. Wink, wink. Exactly. And yeah, so you guys can give each other hints in the chat. I will just be blind and not read it. All right, so let's move on here. I started going through and highlighting all the like important ones I wanted to cover, but I ended up highlighting almost all of them. So we're just going to go through it. And it's going to be kind of fast just because, you know, 50 minutes to do 60 questions is a lot. If you have any questions or you want me to repeat anything, please, please, please say something. And I do expect participation. So, first thing is first, what is the equation for chemical shift calculations? Hertz equal, ppm equals what? Hertz over megahertz, exactly. So here they gave us ppm and they gave us megahertz, which is 400. So we're looking for x right here on the top. We are going to do some basic, you know, algebra kind of multiplication, and we get x equals 500. So D is our answer, and I'm going to actually highlight these in blue. Ta-da! I know this is a huge throwback, but it's really simple once you get the equation down. So next up, what is a splitting pattern in the H1 NMR spectrum? So we're looking at the hydrogen NMR, and we're asking for the bolded hydrogen atom. So this one right here. So let's actually draw this out. We have CH3, CH2O. And we have two of those bonded to CH3 like this. It's really funny looking, but whatever. So the hydrogen that is bolded is this one right here. And we are looking for splitting. So first thing is first. Are we going to split through a heteroatom? No, unless he says this is a pure solvent, but he's only going to do that in lab, right? Not in this lecture. So these red hydrogens have 1, 2, 3 neighbors. What is the splitting rule? Or equation, or whatever you want to call it. N plus 1, exactly. For normal splitting, it's N plus 1. So we have 3 neighbors plus 1 equals 4, which translates to a quartet. So D is our correct answer. And someone said only if he says theoretically, right? And I think that is going back to my heteroatom rule. So if he says theoretically how many is possible, then you might consider it, but he has to say in the problem that it's a pure sample, or we're looking at every possible theoretical hydrogen. And then someone asked a question. It's definitely not a stupid question. It's actually a good question. Is this a good review for the exam? So I think it is. Even if the questions are not 100% exactly like this is showing you what kind of stuff to study. It's a lot of review of chapters 9 through 13. And that's super important because people forget about it. So do all the other practice problems from this semester, but this is also a really good guide, I guess. Okay, so for the next couple, we are looking for spin-spin splitting. And so spin-spin splitting means what again? Tell me while I draw these out. So yes, it's something about the signals, but it means having, yes, anything that is not a singlet, exactly. So anything higher than a singlet. Perfect. So when we're doing NMR and we're trying to count signals, what is the first thing we look at? Starts with an S. Symmetry, exactly. So we have symmetry right here. Here we have internal symmetry, so these three are the same. And here we have internal symmetry so that these two are the same. Perfect. So if there is symmetry right down the middle, what is the relationship between this hydrogen and this hydrogen? And we're going to use spicy words like, oh, I didn't even have to say it. I'm so proud. Yes, they are homotopic. Exactly. So homotopic means they are exactly the same. So they are not splitting one another. So no, there is no spin-spin splitting. Awesome. All right, so in this next question, number 4, all 9 of these hydrogens are exactly the same. And the next hydrogen is all the way over here. So how many bond lengths do you have to be within in order to be counted as a neighbor? 3, exactly. So if we count this, we have 1, 2, oops. First of all, we have a heteroatom, and second of all, the next hydrogen isn't until all the way over here. That's way, way, way too far. So no, this does not have spin-spin splitting. Last but not least, for this one, we know that all 3 of these hydrogens, or excuse me, all 6 of these hydrogens are exactly the same. And we know that we have these 3 hydrogens over here. What's the difference between 4 and 5, though? Yes, we have a hydrogen here because this carbon is not fully substituted. So this hydrogen right here can now actually couple with these hydrogens. They're within 3 bond lengths. And so is that higher than a singlet now? Yes, indeed. So this is how we do spin-spin splitting. Just for funsies, let's find out what the splitting value, I guess, is for the pink hydrogen. So it has how many neighbors? 6 plus 1 equals 7. That is a septet. Or a multiplet. Awesome. That was going to be my next question. So anything above 5, we just call a multiplet. And so the black hydrogens are going to have how many neighbors? Not 0. It does end up being a doublet, and the reason is we have 1, 2, 3. So this pink hydrogen will count as 1 neighbor. So it's 2, and it ends up being a doublet. Oh, yeah. I just realized that both of these sides have black hydrogens. I should have been more specific. You're right. This side would be a singlet because it has no neighbors. You are correct. So I'll leave this up for a second. And swoosh. All right. So now we are on to mass spec. So it's asking which of the following formulas could not arise when we have an M plus of 142. Alrighty, so 142. At this point, what are we looking for? or you know what, even before that, what rule can we not use since this is an even number? Nitrogen, exactly. So usually the question he likes to give you guys is the nitrogen rule. And so if we had an odd number, we know that there's an odd number of nitrogens. But as someone else pointed out, we don't have nitrogens. So we're only going by our molecular weight. So we're going to go through each of these and count the molecular mass of each of these compounds. And we would do that, for example, by saying carbon has a mass of what? 12. They're going to do 12 times 11 plus 10 times 1. And we're going to go ahead and do that for each of these. So 12 times 10 plus 8. 8 times 1. And then what's the mass of oxygen? 16. Sweet. I don't want to actually do the math on all of these, so has anyone done the math? I mean, I can do it if I must, but... So, yes, all right. So someone said that all of these equal 142 except for B, which equals 144. So again, we are looking for which one could not arise, which means B is our correct answer since it adds up to 144 and not 142. Sweet. Any questions about this one? All right. So which element contributes significantly to the M+1 peak? So let's review. What is the base peak? Base equals tallest. Sweet. What is the molecular ion? It is the molecular weight, but what's another name for it? It is the M+, exactly, which is the molecular ion, which is the full mass. Sweet. So M+1 versus M+2. I think M+2 might be a little bit easier to remember. What is counted in the M+2 peak? Bromine, chlorine. 2 more. Oxygen, and 1 more, sulfur. Sweet. Oxygen and sulfur are super tiny contributors, but they are part of M+2. And then there are 3, actually, that contribute to M+1. Do you guys remember what they are? Nitrogen, carbon, and hydrogen. Exactly. Cool. So now that we have reviewed all of that, the thing that's important about this question is which element contributes significantly? So out of nitrogen, carbon, and hydrogen, which one do you think has the most significant contribution? Carbon. Perfect. And someone said, what was the answer to the last question? It was B. And yes, someone answered my next question, which is the reason it's C, or carbon, is because of the carbon-13 isotope. Perfect. So I'm going to scroll a little bit. All right, so the mass spectra of alkyl bromides and chlorides are characterized by an intense peak at where? We just covered this. That's another way of saying the same thing. D, M+2, exactly. Same question, just slightly different wording. All right. I hate this question with a passion because when I took this class, it was so tiny, you couldn't see it, you can't see any numbers, so annoying, right? But now we have it virtually, so it's like slightly less terrible, even though it's like one whole pixel. Anyway, that was my rant. It had to happen. So if we look over here, we have a little reference for all of our peaks, right? And they're asking for the base peak, so we know that we're looking for the tallest one. In this case, where approximately is the tallest peak found? Yes, 29, because we can see that right here is 30. So we want something slightly less than 30, so B is our best bet. So what if I asked you, where is the M+ peak found? Exactly, approximately 44, 45. You can't tell specifically because, it's just in the middle there, but this would be our M+. And so what is this tiny little nub thing right next to it? The M+1, exactly. Do we have an M+2 peak? No. Cool. So what atoms do we absolutely not have in this molecule? Exactly. No bromine, chlorine, oxygen, or sulfur. Perfect, perfect, perfect. So I'll leave this up for like a second. Let's scroll. Okay. So this next question is back to NMR, and it's asking how many different signals you would see, assuming that you have really great resolution and you can see all of them. So I'm just going to redraw this to give myself a little bit more space. And I'm going to try my best to do it in 3D, even though, doesn't work out that well. So first thing is first. What do we always look for first in NMR? Symmetry. Yes. Okay, so symmetry. Bear, shut up. Symmetry is going to be internal for this one. So not across the whole molecule, but right here we can draw a line of symmetry because these two halves are exactly the same. So we can tell that if there's symmetry right here, that means this side and this side are exactly the same, which means, oopsie, all four of these hydrogens should be the same. But what you might be thinking, because it's kind of 3D, is like, okay, well, this one's pointing forward, so it sees the front, while these are pointing back, so they see the back. So shouldn't they be two different signals? Why or why not? Okay, a couple people said no. Because they see the same thing. So yes, that's true. The top isn't symmetrical. So the things pointing forward and the things pointing backwards are the same, or are not the same, right? So how come in this case they're both able to see the same thing? Because they can rotate, exactly. So these two sides are different, but this whole ring will rotate. So for that reason, all of these hydrogens will be exactly the same. Perfect. All right. So let's go up one. What do we think about the hydrogen here? Where? Exactly. There is no hydrogen. So this carbon right here does not have any hydrogens. I always have students who accidentally put a signal here. Remember, only 4 bonds per carbon. Okay, moving on. So here we have 2 hydrogens. Here we have 3. And at this point right here, we have a potential chiral center, right? So this is important because we might have enantiotopic or diastereotopic hydrogens here. What would we need in order for them to be diastereotopic? Yes, we would need a chiral center already present somewhere else. And unfortunately, or fortunately, we do not have one. So these are going to be enantiotopic, which means they will just be 1 signal. So this will be signal number 1. Or, you know what, we count the blue signals as number 1, so that'll be number 2. So next up, these 3 hydrogens, what do we think? Are they going to have any kind of relationship with anything? So the question is asking for carbon NMR, but I want to do both with you guys really quick because I know people struggle with this one a little bit. But that's a really good question. I'm glad you guys questioned that because it is carbon NMR and we were doing hydrogen NMR. So I'm glad you caught that. So this will be signal number 3. And then nothing too special over here. But here we have our double bond. And this is where a lot of people get tripped up. So in order for 2 hydrogens on a double bond to be diastereotopic, what are the rules, I guess? Bear's having the time of his life. Let's just ignore him. Okay, so you guys might have forgotten, but that's okay. Okay, you guys got it. So yes, they have to be on the same carbon, and the opposite carbon must have 2 unique substituents. So do these have 2 unique substituents? Yes, they do. And so these 2 are attached to the same carbon. So they are diastereotopic. But what about the relationship of this purple hydrogen to the black and pink hydrogens? What is their relationship? They're just plain old heterotopic, exactly. If they're not on the same carbon, they can't be counted as diastereotopic. Perfect. All right. So in this case, the purple hydrogen will be signal 3. Pink will be 4. Just kidding. I can't count, apparently. The purple hydrogen will be signal number 4. Pink hydrogen will be signal number 5. And the black hydrogen will be signal number 6. So on a hydrogen NMR, you would have 6 signals. The carbon NMR is a little bit easier. So if we start in the same place we did before, these 2 carbons are exactly the same. So that will be signal number 1. And then up here, we have signal number 2, because even though it doesn't have a hydrogen, it still has a carbon, obviously. So this is signal number 2. Next up, signal number 3. Signal number 4. Signal number 5. And last but not least, signal number 6. So something that trips people up sometimes is the fact that there's 2 hydrogen signals on this carbon, but only 1 carbon signal. So remember that carbon NMR can't have diastereotopic and enantiotopic. That is strictly for hydrogen NMR. Okay, this one took a little bit. Any questions, comments, concerns? Do we kind of sort of remember how to do this stuff? Yes? Okay, good. That's always good to hear. Kinda. Kinda is good. At least it's not completely gone. Alrighty. So furthest downfield versus upfield. You guys already know. So we have the red arrow and the blue arrow. Which side is downfield? Exactly. So the other side has to be upfield. What's another word for downfield? It also starts with a D. De-shielded. Oopsie. Exactly. And so the other direction would just be shielded. All right. So I'm going to trust that you guys have the little NMR regions cheat sheet thing that I gave you guys. So please tell me, which of these would be the most downfield? Ooh, good. Okay. So I'm glad you guys picked up on it, even though I didn't highlight it. So we are looking for carbon NMR. There is a difference between carbon and hydrogen NMR. And it's important for you to note that we're talking about these carbons in each case. And you guys are absolutely correct. The ketone will be the most downfield or de-shielded. Perfecto. All right. Going down to number 12, HA and HB are related how? First thing we ask ourselves, is there a chiral center on this molecule? No, there's a potential chiral center, which is right here. So the other option, are these 2 on the same carbon of a double bond? No, so we can automatically rule out diastereotopic. Have we ever learned about isomeric protons? Like, what even is that? It will go away. Okay. So now we are looking for the best answer. And students always mix up vicinal and geminal. Which term means on the same carbon? Is it vicinal or geminal? Geminal, exactly. Vicinal would mean on carbons next to each other. So B is also out. So between homotopic and enantiotopic, which one is the best choice? C, because that is the most specific. You are absolutely correct. And then someone had asked which one would be the second most de-shielded. I believe it would be A, but I have to look back because I know there's a little bit of a thing with triple bonds. But I believe it would be A. Okay. We're going to skip those because we did really similar ones. All right, so you guys kind of already told me this, but vicinal coupling is what? A, exactly. This is one of those questions that are like a freebie point. Like, it's good to know. Alrighty. This is one of my favorite questions from chapter 19 to do because they look really scary, but they're not. So it's asking two singlets only. So we only have two signals. First thing we're going to do is go through and assign symmetry. So that one, that one, that one. This one has it right down the middle. And we have symmetry right there. And I'm going to start with the most symmetrical one, just because I know the more symmetry, the fewer signals you have usually. So starting here, we have 1, 2 signals. Cool. And so let me draw out 1 hydrogen each. Do either of these hydrogens have another hydrogen within 3 bond lengths? No. So does number 5 work as 2 singlets only? Yes, it does. So I am happy with that answer. I hope you guys are as well. Cool. Okay. All right, this one should be real quick. Which of these is conjugated? B, exactly, because remember, conjugation means 2 double bonds separated with a single bond in the middle. Ooh, one of these reaction coordination diagrams. So this is our activation energy. This is our potential energy. The one with the lowest potential energy is the what product? Thermo. The one with the lowest activation energy is what product? Kinetic. So in this case, A is the kinetic and thermodynamic product. So we know that that's favored at equilibrium. So we know that the more stable product is formed more rapidly. And I'll zoom out so you guys can take a look. Any questions on that one? Also, I forgot to send the attendance link. So pretty please sign in. Heart. Okay. So what kind of reaction? Oh. So someone asked, in what case would they be different? So let's say I had something like, nope. So here we have activation energy and we have potential energy. And again, we're always talking about lowest. So the lowest potential energy is going to be the thermodynamic product. So that's this one. And the lowest activation energy is the kinetic product, which is this one. So in this case, the less stable product would form the most rapidly. You're very welcome. Okay. So what kind of reaction do we have here? We have a diene reacting with a random looking double bond kind of thing. Diels-Alder, perfect. All right, so our little cheating version of Diels-Alder will be, wow, that's so ugly, it makes me sad, that's okay. We're going to use the double bond that is not a carbonyl. So it's going to look something like this. Right? Something like that. We don't care. So the biggest thing here is, actually, no, I messed up. I forgot a carbon. No, I didn't. I had it right. I don't know why I'm like this. Okay, anyway. We know that we are going to make a 6-membered ring. And we also know that because of this tip, we have 1 carbon in the bridgehead. So we can automatically get rid of this one because, like, what in the world is that thing? Ew, I hate that. Why does it look like that? Why is there a 4-membered ring? Ew, I hate that. All right, the next 2 look okay. We have 1 versus 2 in the bridgehead. Which one are we picking as our answer? 3, exactly. Questions, comments, concerns? That's the quick way to get through Diels-Alder. All right. So we're going to do 21 now. So this molecule that we have drawn is an ester. So what reagent must we use which must we use to be able to reduce an ester? Yes, we have to use the strong one, so LiAlH4, which means, what about NABH4? Is that one capable of reducing it? No. So even though you haven't seen answers C and D in this class, you already know that NABH4 does not work, therefore that is the correct answer. Okay. So I want to go over this one because I don't believe we talked about it, but this does usually show up. So it's a really easy question. I don't want you to get it wrong. So if he asks you for this, like, intensity of absorption stuff, he's referencing Beer's law, and you don't really need to know anything about Beer's law besides what each of these signals mean. So A is absorbance, the E looking thing is molar absorptivity, C is concentration, B is length of light. Usually he asks you for this guy. So your correct answer is C. Phew, that was fast. All right, so moving on. All right, this is another one that we didn't completely talk about explicitly, but if we are doing a reaction such as 1,3-butadiene with HCl, we can completely rule out the answer that has the hydrogens directly attached to the double bond. So in this case, which one is directly attached to the double bond? I'm sorry, the chlorine cannot be attached to the double bond. E, exactly. So in this case, the chlorine and the hydrogen are attached to the double bond. That is not going to happen. So E is going to be the correct answer. The correct wrong answer. Alrighty. So we've done that one before. I really wanted to cover one like this because it is a multi-step one. So PBr3, real quick, what does it do? Protecting group, and it turns OH to a Br. MgBr, Mg is what? What kind of reaction? Grignard. Sweet. Okay, and this is a what? Or an what? Epoxide. Sweet. Okay, so then we have acid, whatever. So we are going from OH to Br to MgBr, which just means we have a what charge on that carbon? A minus. So we have this negative charge coming in, right? So where are we going to attack? Keeping in mind, we do not have an acid catalyst. The less substituted side, exactly. Cool. So we're going to attack, bam. We're going to open up the epoxide. So it goes bam, bam. Here we have attached to one carbon. This carbon is bam, bam, bam. And right here we have attached an O minus. And the acid is going to be used to protonate that. And I'm not redrawing it again, so duplicate. And we add a hydrogen. So which one of these bad boys looks like our answer? If it was drawn slightly prettier. Oh, sorry, I didn't see that you guys had responded. Yes, it is C. Ta-da! Any questions on this one? All right. So it is technically 151. So yes, when there is no catalyst at all, we're going to attack the least substituted side. Precisely. You're very welcome. Okay, guys, so I'm going to send the attendance link one more time. And I'm actually really sad that it's over. But you guys have been really, really great. I hope you have a wonderful day and a wonderful weekend, and good luck studying. And hopefully I will see you guys at the exam review next week. If not, I'm sure you're going to do amazing. And I wish you good luck with everything in your future. Bye.